Hi, in this video we're going to go over the series divergency test and certain properties of series. So first, what is the divergency test? Well, notice that if the series sum from n equals 1 to infinity of an is convergent, then you're going to have that the limit when n goes to infinity of an is equals to 0. That's something that is always going to happen with a convergent series. Now, it is important to notice that this theorem implies that if the limit when n goes to infinity of an is different from 0, then the series diverges. And this is what we call the divergency test. If we can get a series and we can check up that the limit of the sequence is different from 0, we know right away that that series is going to be divergent. However, having the limit when n goes to infinity of an being 0 is not enough to imply that the series converges. And so that's going to be the case of the harmonic series. So with the harmonic series, or the series from n1 to infinity of 1 over n, when we check the partial sums, we're going to check that the partial sums are always bigger than a certain amount. So for example, s of 2 is equals to 1 plus 1 half. And when we start checking out bigger partial sums, so for example, s of 4, we're going to have that is bigger than 1 over 2 over 2. S of 16 is bigger than 1 plus 4 over 2. And in general, s of 2 to the k is going to be bigger than 1 plus k divided by 2. So what this means is that if we can make s of 2k go to infinity as k goes to infinity, we can pretty much say, well, the series is going to be divergent. Notice this when we take the limit when k goes to infinity, this means that it's always going to be larger than infinity. So this means that this partial sum are going to be going to infinity, and the series overall is going to be divergent. Now, notice that if we take the limit of the sequence 1 over n, that is 0. And so that implies that it's just not enough to have 0 on the limit of the series to prove that the whole series by itself is going to be convergent. Now, let's take a look at some other series and some other properties before we actually jump to some examples. So the first type of series that I want to check is the telescopic series. This type of series is going to have a very particular shape. So it's going to have the shape series of n equals 1 to infinity of an plus 1 minus an. And notice that when we take the partial sum with respect to certain number n, then that's going to be the sum of 1 up to that number n of an plus 1 minus an. And when we actually go ahead and compute those, we're going to get the end result minus the initial. So let's see why that is true. So notice that if we do sum of n equals 1 to n, then I'm going to start with a2 minus a1 plus a3 minus a2 plus a4 minus a3 plus a5 minus a4. So notice that I'm always getting these numbers cancel. So this cancels here and this cancels here. And so at the end, I'm just going to have the first term plus the last one. And that's what's happening when I open up and see some of the terms of this sum. And so at the very end, we're going to have that, of course, the partial sum is going to depend of that. And if the partial sum depends on that, then, well, I can take the limit when n goes to infinity. If this is a nice sequence and this term actually has a limit, then the series is going to be convergent. Okay, and one of the examples that we can take for that is the following series. So consider the series for an n equals 1 to infinity of 1 over n plus 1. By itself, the series is kind of hard to check. Notice that the limit when n goes to infinity of 1 over n plus 1 is actually 0, so I cannot tell anything by it. But what we're going to do is we're going to open this to be rearranged, and we're going to rearrange it by partial fractions. So if I use partial fractions here, notice that this is going to be 1 over n minus 1 over n plus 1. I'm going to skip the part of finding the numbers here. You can do that if you prefer to, but essentially I can just check that 1 over n times n plus 1 is 1 over n minus 1 over n plus 1. Now, so that means that I can rearrange this as this, and it's not really the same as what we had before, because we have an minus an plus 1, but it's kind of like the same thing. You can flip it around if you want to. If you want to have the minus here, you can just put a minus outside, factor that out, and you're gonna have 1 n plus 1 minus 1 over n. And so in this way, now you can see, oh, okay, I have the an plus 1 term minus the an term. And so essentially, by the principles of the telescopic series, this is going to be equals to just checking the limit when n goes to infinity of 1 minus 1 n plus 1. Notice that that is going to go 0 here. So this n here is going to go to 0, and so this is just going to be 1. And so this telescopic series is going to be convergent. Okay. You got to be extra careful when you are trying to figure out what is the first term and what is the last term that you're going to have on this series. In particular here, on this scenario, it might be a little bit easier to just check. So for example, you start with the first number. This is 1 minus 1/2 plus, and then n equals 2 is 1/2 plus 1 over 3, then plus, minus, then 1 over 3 plus 1 over 4. So you can clearly see which ones are going to be canceling out. And so that's why you know that this is going to be 1 minus 1 over n plus 1. But it's always worth actually doing a couple terms to know what is the first term that is going to be left and the last term that is going to be left. Now, some extra properties of the series had to do with the convergence here. So we already have information about an and bn being convergent series. Then there's a lot that we can say about the multiplication by a constant of one of the series, the sum, and the subtraction. And as you can imagine, the multiplication of a scalar times a series that is already convergent is not going to make a lot of difference. I can just pull out the constant, and that's still going to be a convergent series. And if I have the series of the sum of two sequences, but the individual sums of those are going to be convergent, then all those sums, I can split this big sum into the sum of each of the components, and since each of them is convergent, then the sum is going to be convergent. And of course, the same thing happens for the subtraction. The subtraction of two convergent series is just going to be the difference between these two convergent series. And because these two are finite values, then this is going to be a difference of finite values. And then it's going to be a finite number, and the difference is going to be convergent. So now let's take a look at some examples to check on all these properties. So first, we want to know the convergency or divergency of the series. So for the first one, we have 3 plus 1 over 2 to the n, series for an n equals 1 to infinity. Notice that the limit when n goes to infinity of 3 plus 1 over 2 to the n is going to 3. 3 is different from 0, so immediately by the divergency test, this diverges. The limit is not 0, the limit of the sequence is not 0, so immediately diverges. Same thing happens with the second one. We have the sequence is this, and the limit when n goes to infinity of 1 plus 1 over n power to the n is actually the number e. So you probably did this exercise before, and if you haven't, it is a good exercise, so make sure that you actually prove that that is true. This is different from series, so this series is going to be divergent. Now, we have a couple more of things that we can check. So for example, for this series, this one here looks clearly like a telescopic kind of situation. And if we start looking at what the type of terms this is, we can get some information of what is going to be left at the end. So notice this is the square root of 2 minus the square root of 1, and then plus, and then equals 2 is going to be square root of 3 minus the square root of 2 plus the square root of 4 minus the square root of 3. So you can kind of see what's going to be left. This cancels, this cancels, so on and so forth. And so we're going to get that this is going to be equals to the limit when n goes to infinity of minus the square root of 1 plus a square root of n equals 1. And because this one is going to infinity, then this goes to infinity. And it doesn't matter that this is that this different series here is a telescopic, is going to be divergent. Now let's take a look to another exercise. Let's see this one here. N equals 1 to infinity of 2n plus 3 over n plus 1 times n plus 2. Has a typo here. So this type of thing has a lot of things going on down below, but this looks like something that I could do with partial fractions. So I can actually go ahead and do the partial fractions for it. So I'm gonna say this is a n plus 1 plus b n plus 2. And so simplifying this out, 2n plus 3 is equals a n plus 1 plus b, sorry, this would be a n plus 2 plus b n plus 1. And I'm going to assume right now that this is not natural, just so I can find more easily these numbers. So I'm going to assume that n belongs to the real numbers, and n is going to be equals to minus 2. And if n is equals to minus 2, this is here minus 4 plus 3 minus 1. And so here this becomes a 0, and this becomes a minus 1 here. So I get minus b. So that implies that b is equals 1. Similarly, if n is equals minus 1, then I get that this is minus 2 plus 3, so 1. And then minus 1 with 1, this is 0, and this becomes a. So a is equals 1 as well. And so that means that this arrangement is just 1 over n plus 1. And then minus 1 over n plus 2. This actually is going to give me that, and the sum of 2n plus 3 n plus 1 n plus 2 is actually giving me some sort of telescopic series. Notice that this is, if this is the an, this is the an plus 1. And so we can do the same kind of thing that we've been doing for evaluating telescopic series. We initially plug this out on the first term. This is 1/2 minus 1/3 plus, and then n equals 2 is 1/3 plus 1/4 minus 1/4. And now you can kind of see the pattern here that this has. 1/4 minus 1/5. And so this cancels, this cancels, this cancels, this cancels. And clearly, this is going to be equals to the limit when n goes to infinity of 1/2 minus 1/n plus 2. Actually, since it's the last term. And this is just going to be 1/2. So this means that this is a convergent series. Okay. So that takes 4 out of 6 of the examples. Now let's take a look to some more examples here. Notice that this series here from n equals 1 to infinity of 7/2 to the n plus 1/2 to the n, this one here. Notice that I can separate this as this one plus this one by properties of the sum of the series. And this is going to be convergent by properties of, the geometric series. But this one, by the same token, is divergent. Since 7/2 is bigger than 1, so this is divergent. So because we have a sum of a divergent and a convergent sum, then this is divergent overall. And that's it. So now we have the last one, which is this one here. We have sum of n equals 1 to infinity of 1/2 to the n plus 3/n n plus 1. We actually kind of saw this one before. So I can separate this as n equals 1/2 to the n plus 3 times the series of 1/n n plus 1. And this is a telescopic series. I can actually find out how much this value is. This is a geometric series. I can actually find out how much this value is. And this is a 1/2, which is less than 1. So both of them are going to be convergent. This is convergent, this is convergent, so this is convergent.